Keyword, intro reveal, carbon nanotubes. In the autumn of 2006, a materials scientist at the Technical University of Dresden named Peter Paufler placed a sliver of metal, the size of a grain of rice, into the sample chamber of a transmission electron microscope. The sliver had been cut with great care from a Damascus sword that had been forged in the year 1640 by a smith named Assad Ullah in what is now Iran. The sword had been in the collection of the Bern Historical Museum in Switzerland since the 1800s. Paufler closed the chamber. He pumped it down to vacuum. What he saw in the next hour would be published in November of 2006 in the journal Nature, in a 3-page paper that would change how materials scientists thought about the gap between modern nanotechnology and the craft traditions of the medieval Islamic world. This is the slow story of that paper. What the microscope was looking at, what it found, and what it means. Settle in. To understand what Paufler saw in November of 2006, you need to understand what a transmission electron microscope sees. A normal optical microscope, the kind that a high school student uses to look at a cheek cell on a glass slide, uses visible light. Visible light has wavelengths between roughly 400 and 700 nanometers. That means an optical microscope cannot, in principle, resolve features smaller than about 200 nanometers. Below that, the wave nature of light blurs the image. You can see a bacterium with an optical microscope. You cannot see, with an optical microscope, the individual molecules of which the bacterium is made. A transmission electron microscope does not use light. It uses electrons accelerated by a high voltage, typically 200,000 volts, and focused with magnetic lenses. The wavelength of an electron at 200 kilovolts is about 2.5 picometers. That is 2.5 thousandths of a nanometer. You cannot, of course, use a transmission electron microscope on a living cell. The sample has to be in vacuum. It has to be thin enough for the electrons to pass through, typically less than 100 nanometers thick. And the electrons cause radiation damage to organic material. The technique is, for the most part, used on inorganic samples, metals, ceramics, the engineered crystalline materials of modern microelectronics. A metal sample is prepared by ion milling. A beam of argon ions, fired at the surface of the sample at a glancing angle, slowly wears away the surface until a small region in the center is thin enough for the electrons to pass through. When the electrons pass through the sample, they scatter in patterns that depend on the atomic structure of the metal. The diffraction pattern that results is the signature of the crystal structure. The image that results is a direct view of the atomic arrangement. Lattice planes visible as parallel lines. Individual columns of atoms visible as bright spots. This is the instrument Paufler turned on. This is what it was looking at when it looked at the Damascus blade. The Damascus blade that Paufler examined was not a museum-quality unique artifact. It was a working sword, of fine but not exceptional quality, made in the 17th century by a smith working in what is now Iran. There are tens of such blades in European museum collections. They are dated, where possible, by the inscriptions on the blade, by the style of the hilt, and by provenance records that go back through generations of private collectors before the blade reached the museum. The Bern Historical Museum agreed in 2004 to allow a destructive sampling. The museum's metallurgical curator selected a region near the handle, a region that is structurally non-load-bearing on a sword, that does not affect the visible polished face, and that, if removed carefully, leaves no visible damage. From this region, a sliver about 3 millimeters long, 0.5 millimeter wide, and 1/10 of a millimeter thick was cut, with a low-speed diamond saw underwater cooling. This sliver, this very small piece of 17th century Syrian steel, was the entire sample. It was packed in a sealed glass vial and carried by hand to Dresden. At Dresden, the sample was prepared, the ion milling, the polishing, And then they started looking. What they saw in the first hours was the cementite layers. These have been known for 100 years. Damascus steel, viewed under any decent metallographic microscope, shows alternating bands of dark and light. Bands of cementite, which is the chemical compound iron carbide, alternating with bands of ferrite, which is essentially pure iron. The bands are responsible for the watered pattern that is visible to the naked eye on a polished and etched blade. This was not the finding. This had been known since the 1880s. The finding was what was between the cementite layers and what was inside the cementite layers when you looked at high enough magnification. At magnifications of roughly 100,000 times, the cementite layers in the Damascus sample resolved into structures that no one had previously documented in a historical steel. First, the cementite was not, as had been assumed, a continuous layer. It was made of long, thin, parallel filaments. Wires of iron carbide only a few nanometers across, running in the direction of the forging, like the strands of fiber in a bundle of rope. These were what materials scientite nanowires. Modern composite materials, developed in the 1990s and 2000s for high-strength applications, sometimes contain similar structures, deliberately engineered. Second, between the cementite nanowires, in the regions of softer ferrite, there were tubes. Hollow cylinders, only a nanometer or two in diameter, made of pure carbon. These were carbon nanotubes. Thous. Carbon nanotubes had been first synthesized, first deliberately made by a human being, with the intention of making them. In 1991, by the Japanese physicist Sumio Iijima, at the NEC Research Laboratory in Tsukuba. Iijima had been studying the residue produced by the carbon arc method, which had been developed in the 1980s for making fullerenes. He found in the residue By 2006, 15 years after Iijima's paper, carbon nanotubes were one of the most actively researched classes of nanomaterials in the world. They have extraordinary mechanical properties, tensile strengths far higher than steel by weight, and they have unusual electrical properties, conductive, semiconductive, or insulating, depending on the chirality of the rolled sheet. Materials scientists in 2006 knew, in principle, how to make them. The methods involved chemical vapor deposition, high temperature growth on transition metal catalysts, vacuum systems, expensive precursor gases. The methods were difficult. Paufler found nanotubes inside a sword made in 1640. The sample was old enough that the question of contamination was immediately raised. Had the nanotubes formed in the sample preparation? Had something gone wrong in the lab? Paufler addressed this in the paper. The nanotubes were embedded in the bulk of the metal, not on the surface where preparation could have contaminated. They were present in multiple separately prepared samples from the same blade. They were present in samples taken from different regions of the blade. They were not present in a control sample of modern steel that had gone through the same preparation steps. The nanotubes were really in the sword. The mechanism by which the nanotubes formed in the Damascus blade is not, in 2026, completely settled. The leading hypothesis, set out in Paufler's paper and refined in subsequent work, runs as follows. When wood steel is forged at very specific temperatures, the smiths called this the singing forge, because the metal makes a particular high-ringing sound when the hammer strikes it at the correct heat. The carbon atoms in the iron migrate, slowly, into bands that segregate by alloy chemistry. The trace amounts of vanadium and molybdenum, which were carried into the original Wootz ingot from the soil that nourished the leaves in the Indian crucible, act as catalysts. They lower the activation energy for the formation of certain carbon structures at temperatures around 800 to 900 degrees Celsius. Under those conditions, with those catalyst atoms in those concentrations, the carbon can rearrange itself into nanotubes. It is the same chemistry, fundamentally, that occurs in a modern chemical vapor deposition reactor. The temperatures are similar. The catalyst metals are similar. The carbon source, methane in the modern reactor, organic compounds released from the original leaves and charcoal in the medieval crucible, is chemically equivalent. The smiths of Damascus, working in 1640, were running, by intuition and inheritance, a chemical vapor deposition reaction. They were producing, at the small scale of the local carbon distribution in the steel, a composite of cementite nanowires and carbon nanotubes. They had no theoretical framework for any of this. They had 1,000 years of master-apprentice tradition that, when followed exactly, produced a blade with the properties of Damascus. This is the strange particular finding of the Paufler paper. Damascus steel is, by the standards of 21st century materials science, a nanocomposite. The smiths who made it were not aware that they were producing a nanocomposite. They were aware that they were producing a blade, and they passed that knowledge down for 1,000 years, until the supply chain broke and the knowledge was lost. The Paufler paper, in November of 2006, did not recover the technique. It did not allow anyone to make Damascus steel again. The original Wootz ingots, with their exact trace element fingerprint from the Indian soil of 1,000 years ago, are not in the ground anymore. Modern smiths can come close. They cannot, yet, reproduce the original exactly. But the paper did something else, which is what it is remembered for. It demonstrated, conclusively, that the gap between medieval craft and modern nanotechnology is not as wide as we had assumed. That the smiths of Damascus, working 350 years before nanotechnology was a word, were operating at the nanoscale. The microscope. In 2006, new. In 2000. Two. Fine and six. The Paufler finding, since 2006, has changed what materials scientists look for when they examine historical metals. The technique that he applied, transmission electron microscopy on small samples taken from museum artifacts, has now been used on Japanese tamahagane sword steel, on the Iron Pillar of Delhi, on the high-quality Roman gladius blades from the 1st century, on Viking pattern welded swords. In each case, scientists have looked for, and sometimes found, microstructures that suggest the medieval and ancient smiths were running processes more sophisticated than we had given them credit for. The general lesson of this work, across many traditions, in many centuries, is that craft knowledge, when it is honed by master-apprentice transmission across many generations, can produce engineering outcomes that match what modern theoretical science can derive. The two paths are different. The craft path is empirical, slow, inherited, and dependent on the unbroken continuity of practice. The theoretical path is analytical, fast, written down, and reproducible by anyone with the equipment and the paper. Both produce real engineering. When the craft path is broken, when the supply chain fails, when the apprentices stop coming, when the master dies without finishing the demonstration, the craft path cannot be restarted from notes. We can, with great effort, reverse engineer some of what was lost. But we cannot, in general, exactly recover it. That is the small, quiet thought to fall asleep on. There is, embedded in a museum case in Bern, in Switzerland, a sword made in 1640 by a smith named Assad Ullah. The sword contains carbon nanotubes that he did not know he was making. The microscope, 370 years later, found them. And we still cannot exactly make the sword again. Sleep well.